move to the main event of today. We'll have the first keynote talk will be provided by Dan Stanzione. So he's the Associate Vice President for Research at the University of Texas at Austin and Executive Director of the Texas Advanced Computing Center. We had a quiz, Dan, on you yesterday night in the trivia game, okay? So he's a nationally recognized leader in HPC. Many of you know him. He has been involved in supercomputing for more than 30 years. He's the PI for a number of NSF supercomputers, including the current Frontera system, which is the fastest supercomputer at a US university, and is leading the upcoming NSF leadership class computing facility. Stanzione received his bachelor's degree in electrical engineering and his master's degree and doctorate in computer engineering from Clemson University. So every year, I think, I don't know, Dan, we might give you next year, I think might be 10 such keynote talks you have given at MOG. I don't know, I need to count. Almost. Yeah, so Dan always gives very fresh perspective on the largest system he's deploying and his experience on that. And I really like your title today. Okay, you want to give a mug shot of the NSF TACC horizon. So with this, let's give a big hearty welcome to Dan.
Yeah. There we go. Sound all right? Okay. I hear echo. Is it okay? Sound all right? All right. Thank you, DK. Thanks, Dave. It's great to be here. As DK mentioned, I feel like I've been to most of the MUG events at this point. I don't know how many I've missed, but 9 sounds right. That's good out of 14. I'm doing all right. It's great to be back. I've tried to sprinkle answers to future trivia questions liberally throughout the talk, for those of you who were at dinner last night. I didn't have the heart to tell them that technically Horizon is deployed just across the border of Austin into Round Rock, Texas, but we're not going to count that. So if you weren't at dinner, what city is the machine in was one of the trivia questions. So I like that it was referred to as Dan Stanzione's machine. NSF might argue, but that's how I feel about it, so that's good. So today I'm going to give a talk that is part sort of overview and update on where we are with NSF things, part some technical on the actual details of benchmarking and deployment and how we get one of these things to full production and working, and mostly opinions and rants about the sorry state of our industry at the moment, where AI is slowly burying all of us. So, but before I get into all of that, let me just say it's the 14th MUG. I think it's over 20 years that we've been working with the MVAPICH lab, but TACC, the Texas Advanced Computing Center that I lead, turned 25. It says this month, it was in June. And I just didn't change the slide, but we've been operating as TACC, although UT had previous computer centers that occasionally would sort of fall apart and get put back together, going back to the 60s. But it's been TACC for 25 years. We've had sort of one account database in that time. So I can tell you we've had more than 1/8 of a million people through the systems in that period, 125,000 distinct users. Only 4 of them got Nobel Prizes. I feel like that's a low percentage. We'll have to work on that. 4 out of 100,000, but still 4 Nobel Prizes, I think 6 Gordon Bells in that span, many other prizes along the way. If you took our 4 big systems and you just sort of divide jobs by their active lifetime, we get a new job every 7 seconds. And in any given year, we have about 20,000 active users, which is the same 5,000 faculty from 2001, and then 15,000 new grad students turning over about every 4 years. Many of them from here. DK, I don't know why you bother when you introduce speakers of networking and saying they were a student here once, because we all just assume that if they're working in networking anywhere in the industry, at one point they were a student here. So anyway, we're proud of what we've done. We're also proud of this collaboration. And again, I give a version of this slide every year here, but it's Incredibly important that we have the MVAPITCH team on board. We, have actively put them into our grants through going back to Ranger, Stampede 1, Stampede 2, Frontera, and now Horizon, spanning, I guess that's 2006. So 20 years exactly at this point, right? Since we started this collaboration, whether it was an Intel system, an AMD system, an NVIDIA system, whether we had OmniPath or InfiniBand, actually have more processors and networks now that I think about it, on the systems, we've always wanted to have the compiler in the stack the vendor gives you, and then the one that's done here, that is the open source one. And it's just been immensely valuable, one, because usually this is the higher performing one, but also because it's just incredibly valuable in understanding, what's hardware, what's software to tune and debug, to have more than one stack, so you can figure out whose fault it is. And that's been huge. So, hopefully this collaboration will go on for decades to come. So the machine I want to talk mostly through the deployment of and sort of the issues around, and I'm going to take several substantial tangents, is the one we built for the new leadership class computing facility. I've been previewing this for a couple of years in talks here. That is the actual building that the LCCF is in. There's actually now a second data center beside it because data centers proliferate. I think they're like rabbits somehow, but where there's one more pop up, but it's now a 200 megawatt data center campus, which 10 years ago we would have thought of as huge, and today we would define as small, given the scale of AI. But that building has 85 megawatts. We have the 20 megawatts sort of on the left side for LCCF. It was sort of halfway through build out from a concrete shell when I was here last year. This year we have machines on it I'm going to show benchmarks on. But the point of the leadership class computing facility is for NSF, the National Science Foundation here, to have a long-term footprint in computing, where there are machines, whether we operate them or not, that you can count on being there in 10 years and 15 years and 20 years, so that we can sort of pair the machines with the long-term science missions. So again, we'll go through that. I will say that building this machine, we'll get into some of the details, is far and away the most complicated deployment we've ever done for a number of reasons. It is in the worst possible market conditions that you can imagine for deploying a machine. Since this was all easier before Microsoft was spending $500 million a day on hardware. It's to do probably the most complex range of science and engineering. Everything is AI plus simulation now, plus experimental data. And then the government, through 4 presidential administrations, has been super consistent and easy and straightforward to deal with. So, as you might imagine. So, by the way, if I'm talking, you can safely assume it's sarcasm. So we have a bunch of partners in this. We have 4 other sites that are getting hardware around the country, each with their own sort of focus, from Atlanta to Illinois, Pittsburgh, and San Diego, each with slightly different hardware. And then we have a few other really important partners here at Ohio State, provide our network stack. I suspect DK is going to talk about this in the next talk, so I didn't bring very many graphs from it, but using one of our early systems, an NVL72 Blackwell cabinet, the latest beta release of MVAPITCH Plus has Blackwell with NVLink support that we'll be using on Horizon. I think DK sent me an email about that like last Thursday. So this is an active collaboration, I would say. We work with Cornell for online training content. We have a bunch of vendors who participate, but for Horizon in particular, NVIDIA, Dell, VAST, Cambridge, Sabi provides the data center. And then we have a bunch of others and some of the ancillary systems around it. First big tangent here. We talk about the market. I will say this is the first time NSF has ever let us carry a contingency budget, and that was a good thing because we needed it. Although, no amount of contingency can deal with the scale of price changes we're all seeing. So this chart I got back in February, so it's hopelessly out of date, from the guy who runs Vidura, Ken Claffey. But this is just tracking the price of various 30 terabyte drives, whether hard drives or TLC or QLC hard drives, from fiscal quarter, so call it like February of 2025 to February of 2026. There's been roughly one more doubling since then because now it's August. But you saw that in a year, price of, take the left-hand column here, the price of a 30 terabyte TLC went from 3,000 to 13,000. So that's a little over a factor of 4. Last time I looked, it was more like 22,000 for a little ruler drive. They weigh about 2.5 ounces, so they're easy to walk out of a data center, and we have 7,000 of them, and they're $22,000 a piece, which puts them at, I don't know, 70 or 80% higher per ounce than gold. GPUs are about 5 times the price per ounce of gold, so racks of gold bars still seem like a good, cheaper idea. Than building computers, even hard drive prices went up about 50%. They have also since doubled for mechanical spending. So we're looking at, 700% inflation in the price of storage in about 16, 18 months. RAM is pretty similar. If you look back, and I've gone through Ranger all the way forward, most systems in a big cluster, you got enough volume and enough discount, we were paying $6,000 or $8,000 per node when all was said and done. An NVL4 board in a Blackwell system is more like 120K. A true NVL4 is 2 Graces with 4 Blackwells. That's about 240K at this point. So we're going from 6,000 a node to 240,000 a node, which means even if you have constant dollars, you're buying what, a 40th to a 60th as many nodes. And the user experience you create on systems, the amount we worry about scaling, the size is very different. If you take your fixed budget, instead of getting 150 nodes in a cluster, you get 8. You worry a lot more about sharing. You worry a lot more about wait times. It's crazy. So yeah, so memory is now running at about 500% of last year's price. Storage is at 700% of last year's price. All of that sounds bad, but if you think about it, well, 2 things happened on the CPU portion of Horizon, the port we haven't deployed yet, which is a bit of a problem, and where the DIMMs couldn't be pre-bought because they didn't exist, LPDDR SOCAMs. When we ordered the system, we had about $9.5 million set aside for memory on the assumption it was $4 a gigabyte. It went to $20 a gigabyte, and because the price is so high, they stopped making low-density DIMMs to maximize profit on every wafer. So we can't get 32 gigs. We have to put 64s in to go to a terabyte. So that moved the decimal point on $9.5 million to $95 million in 8 months on the price of the RAM in the system. So for those of you who don't typically keep an extra 80 or 90 million lying around, it's kind of a big deal. So, and then of course, it used to be you could buy a 2 GPU server for $20,000 in 2021, and you could actually plug it into normal power and cool it with this thing called air. But today, if you buy a typical server, not only do you need 150K, but you need about $500,000 of cooling infrastructure to plug in the first one, and you scale out from there. So this is really mostly just a simple supply-demand imbalance driven by the AI craze. If you look at the worldwide server market in about 2020, it was about $100 billion for all the servers on the planet. This year, the big 4, just the hyperscalers, are spending $750 billion on AI infrastructure. There are very few industries that can grow that fast that aren't software, right? If you have to actually build something, that's really a challenge. And I think for us, it's important to know that yes, it's a price increase, but in many ways, it's also an existential threat to what we do in academic computing and what many of you do. Let's leave aside that the state of funding federally is somewhat precarious. I have whole rants on that. Some of you may have heard them at various places. Somehow I have not been fired over one of those yet. But we're actually in a situation where we've been able to mask a lot of that because most states and universities right now are desperate not to look like they're falling hopelessly behind in AI infrastructure, despite the fact that anything they do is not $750 billion and therefore a drop in the budget. But that's offset what we've lost in sort of federal funding on the hardware side at this point. The users don't have any money, but details. if you have in-room mortar systems that can take propylene glycol CDUs, if you're looking at buying Vera Rubin in, say, an NVL72 form factor, 72 nodes, maybe throwing a little storage next to it, one rack is $9 or $10 million, right? Just the raw hardware without chilling, without storage, without external network is $8 million. Ask me about top of rack switches and standard configurations later, but I shouldn't say that out loud. But right now, if you ordered it today, if you're lucky, you might get it in 9 months, but you're probably looking at 18 months from the time you order. When you get it, there won't be any spare parts for it that you can get inside of 3 months. So when a node goes down, you know, it's going to be a while before you can find parts to fix that node. So we just buy them with extras, which makes the problem worse. But then those fail and you get to it. You can buy a mostly crippled RTX with no 64-bit and no NVLink and no unified memory and all that stuff with an x86 chip, which means you need a completely different software stack and completely different optimizations. And you can get that for a mere $200K at the moment, although those are air-cooled. And if you've ever heard one run, you don't really want to be within 50 feet of it at any given time. So they scream like a banshee. You know, it will cause a stroke in about 10 minutes, I think. So if you're making an order and you're not ordering at $1 billion, your order does not matter. And trust me, I made a $100 million order and nobody cared about that because it wasn't $1 billion in the past year. So even if you're ordering at $100 million, they don't care because certain large vendors, some of you may be in the room, whatever, but the 3 people who really can sell servers in the country are all some tens of billions behind in their deliveries, and several thousand racks back in what they need to get out the door. So you can get the inside story on the day Elon Musk showed up at Dell and the number of things they like took off FedEx airplanes to meet his order that were going to other customers and things like that. It's a very interesting story that's not very public. But the $1 billion stuff is a big problem. CoreWeave sends Dell like a $3 billion purchase order every other month with no terms and sort of empty unit pricing. So for us, you know, we're here to talk about networks and network software. I worry a lot less about trying to scale things to 1,024 network endpoints when nobody can afford 1,024 network endpoints, right? At this point, if you think about, you need 13 of those Vera Rubin racks to hit 1,000 nodes, right? And VL72, if they're $8 or $9 million a piece, then a 1,000 node cluster is $100 million, right? Who spends $100 million on a machine if you're not working for one of 5 or 6 companies, right? You could also, you know, scale to 1,000 in the cloud. But last time I checked for Blackwell in VL72s on Amazon, it was about $750 an hour to get the rack. Is that the one? Or is that for online folks? I could just walk away from it. But again, if you need 13 of those times 750, then you can run your job for $10,000 an hour. How many academics run $10,000 an hour jobs? Yeah, that's about right. So carry the 1, you might get to 0. So, and then also there's the fact that we also get to own big data centers in this business, which makes you extremely popular with the public at the moment. So, so there are a lot of forces sort of lining up to keep us from doing this. And so if you look at sort of the implications of that for HPC, one, Blackwell systems started shipping in volume to CSPs and no one else roughly in January. The ramp was about 1,000 racks a week when they started putting them out from the ODMs. The end vendors had them later, but there's almost none of those on the top 500 anywhere in the world because nobody who does top 500, even governments, can really get them in a timely fashion. You remember a bunch of announcements back in the fall and then in the spring that, let's say, over in Chicago, there was going to be 10,000 and 100,000 Blackwell systems deployed by this June. You know how you don't hear anything about those right now? Perhaps they've changed vendors in the last month to try and do that, but none of them are actually delivered. Ours is, by the way, but the long story that we're going to go through. But and you know what I can increasingly hear from, say, people building these is, if you actually need them, just go to the cloud. They have all of them, right? So Yeah, if you try to buy one, they tell you to use the ones in the cloud. At the same time, the software stacks are evolving in such a way that sharing is really hard, right? Even just the way we used to share serially, batch-wise, right, in time, doesn't really work well with inference-type workloads, right, which everybody wants to run now. I had one lab who has an export-controlled code, which means they actually can't put it in the cloud for various reasons, at least not without going one more order of magnitude up in cost, come to me the other day and they said, yeah, we have this little inference model that sits in front of our chatbot. All we need is like 1.5 terabytes of RAM in NVLink. So NVLinked at 200 gig of GPU, so maybe 10 Blackwells. And you know, we can share it. We only need to stay resident for about 18 months at a time on the NVLink, you know, or the whole useful part, the first 2 years of the system. But so they were looking for an allocation, and what I told them is what they need is $1 million to do that, which was not what they were expecting, to do their little inference model or their little export controlled, maybe has something to do with nuclear reactors code. So when they're like, no, I just need to sit in the NVLink RAM and not move for 18 months, right? That's fun. How many of those users can you do at a time, right, before you're out of hardware? So if you have a customer, in our case, mostly faculty members for any of the academic centers, and they come to you and they're like, hey, I need some time. And then they say, look, I can throw in $100,000 or 200 or 300 or at this point, 4 million, whatever. You can't get much for that money. If you can get it, you don't know when it's going to show up. Increasingly, and this is my favorite part, price is going to change after you order it, right? So just because you ordered it last year, price of RAM goes up by, I don't know, $95 million from the time you order until the time it's delivered. Very few people are willing to eat that. They're going to come back and tell you, we need something different. So you can't get much. You don't know when it's going to show up. You don't know what you're going to get because the price will change after you order it, and you'll get less stuff than you ordered. Then you can't really share it once you get it. So this is a great business model to be in for deploying hardware at the moment. Remember I mentioned this was mostly rant. I think I'm doing well on that. One of the side effects of that, talking to some of the vendors just in the last 2 weeks, is that apparently more than 50% of HPC procurements across the world are failing. They just cancel them because in the end they can't reach a deal or it doesn't get delivered and they cancel the contract. So worldwide, most deals are failing at this point. So nothing. So on the stuff you can't get, most of the deals aren't actually happening to not get it. More on this a little bit later, but let me tell you what we've done this year against this backdrop, because it's been slower than anticipated, but we have sort of ground through almost everything, at least on the GPU side. So, so things we've deployed since I was here last, we do have the archive up in production. It's more than an exabyte worth. We're still calling it Ranch. I think there have been things called Ranch on the floor since 1986, but so it's maybe the 8th or 9th set of hardware that makes up Ranch. It predates the cloud vendors, except for Microsoft, who wasn't a cloud vendor at the time. They had this thing called Windows 3. We put it up, but you could install it from floppies. Most of you don't know what those are. But the new Ranch has been in production for 7 or 8 months. By the way, if you're a Ranch user, many of you have accounts here, you've been getting emails for about a year about moving your data. Do that, because the old one we're trying to turn off in December. So again, the trend has continued that the new Ranch is an order of magnitude bigger than the old Ranch. So you can migrate any data you want. We don't care, because if everybody migrated every single file, it'd be 10%, right, of the new capacity. So that scaling law still works. So anyway, Ranch is out there. We have, as we move towards Horizon, which I'll talk about in detail at some point during the talk, you know, we've been moving towards, which needless to say is a Grace Blackwell system for the GPU part. We deployed a Grace Hopper system, Vista, that I showed numbers for, I think 2 talks ago, here with Gigabyte, because Dell didn't build a Grace Hopper or a Grace node, which has only come back to bite them like 500 times since then. So, and still, but so we did those nodes with Gigabyte. We have 600 Grace Hoppers that we've had in production for 2 years, a couple hundred Grace nodes. These have been huge in letting us get accurate performance projections for Horizon and in getting the software over and convincing us we could really switch from x86 to ARM without it being a disaster. It turns out that's gone amazingly smoothly, and the tools are actually really mature. We've learned a lot about tuning on those platforms and things like that. There's a lot more to go. Samir, we continue to need help on some of that stuff. So that's been really successful for a couple of years. 6 months late, but now 6 months ago, so we're supposed to be here last September, we did add a GB200 NVL72 rack, Grace Blackwell, to Vista. So that latest MVAPITCH release was tuned on that rack. To figure out, so that added to the fun, multiple GPUs to a node, whereas the Grace Hoppers had one, but it's the first rack where we got to juggle having NVLink connections and InfiniBand connections at the same time. As it turns out, totally predictably, getting your traffic to go across the right network is a thing, matters, and has to be dealt with. It's also the first one where now you're competing between nickel and MPI to get who gets the transport layer there. Also, it turns out that getting the right things has been really, really key to tuning, that we figured it out. So we've been running the VAST clients now in production for quite a while as we figured out swapping out from Lustre to VAST for this next system. One of the big things we're doing on both Vista, which is an InfiniBand system, and Stampede, which is an OmniPath system, both of which have been talking to VAST, relatively modest scales, but out to about 3,000 clients. And we've been working on some inference stuff. I'll hopefully mention again at the end if I don't run completely out of time. I'm going to run out of time at some point. Big pile of slides. So again, as I mentioned, we've been building out the home for this because another interesting thing is, in the good old days of $6,000 nodes, we'd get twice as fast nodes every couple of years, but they were the same power to go twice as fast and roughly the same price. Now we get nodes that are twice as fast at twice the power and twice the price. It's quite the bargain. So that makes you think about lifespan of hardware differently. But anyway, so Frontera, our former big machine that was 8,400 nodes and almost entirely CPU, running LinPack would push 6 megawatts. Most days it runs at about 4.5 megawatts. Horizon's easily double that, right? 13 at peak. We're seeing those racks sit at about 170, 180 kilowatts for the GPU racks of the 220 peak, running most average codes. So again, we worked in Round Rock, Texas, because if you're across the highway from this in Austin, you in Austin Energy, which sets your power rates differently, and power is now an $11 million line item for me in the budget. So where it's $2 million a year cheaper, across the highway, not technically in Austin, changing the answer to trivia questions far and wide. But so we've built out this facility to support 250,000 watts per rack. I will rant about data center politics later, but worth mentioning, by the way, that's the underfloor piping, that's to the chilled doors on every rack. You see it there. That was about last September. By October, we'd put in raised floor reinforced for 6,000-pound cabinets. We'll get into that in a minute. Some extra hookups on the end for the secondary loop that's propylene glycol that gets installed with the rack. So that came later. That's just the primary loop there. We do use a ton of power at this data center. The entire 85 megawatt facility, according to the city we buy the water from, the city of Round Rock, it uses the water of 14 typical residential households. It's on like a 15-acre campus. If I put a housing development in there, I'd use more water, right, by a fair amount. It's all dry coolers on the backside. It's 100 degrees most days in Texas, today included. Certainly just for the 8 months of summer, it's really warm. In the winter, it's only like 75. But we use very little water by comparison. In fact, if those houses had swimming pools, it would use way more water than putting a data center in the same spot. So there are data centers that do horrible things with water, most of them built on the cheap for cryptocurrency 5 years ago. But well-built data centers don't have to be a water problem if you regulate a little and design them right. But we've built out a fairly large space. Some of you know Nathaniel Mendoza, my chief of security. That's him in the back corner. For scale, he's about 6'2". So, gives you an idea of the size of the thing. We have been building out for months now. If you were buying anything, buy every potential part that you would need in the data center way in advance, because it turns out, same market pressure, everything that I've said about why it's hard to get computing parts is equally hard for anything in the data center or construction supply chains. Every fuse, every panel, every connector, every gasket, we have boxes of crazy stuff squirreled away, little rubber pieces you had no idea existed. We actually had to 3D print some connectors for the fill hoses for PG25, which, by the way, is the 5th different size connector you need for a CDU nowadays. One CDU, 5 different size connectors. Brilliant. Definitely a cost-saving measure there. So there's a fill hose that's different than every other size hose on it, and you just can't get them. So we 3D printed them. Was the only solution to do things in a timely fashion on that. You have to use it once to fill it. So it worked. But things like sanitary flanges, the little thing you put on the end of a pipe so you can attach a hose to it with a different, one of the screw connectors, so you don't have to go re-weld the pipe every time you change it. They're a standard part. We talked to a vendor one morning at 10 in the morning. They had 20,000 in their supply chain. When we called them back at noon, they were back ordered 3 months, minus 500 in the supply chain. So in 2 hours, 20,000 disappeared. So just because it's there now doesn't mean it's going to be there in an hour. And then it was like, yeah, we need 4 months to get those. So, and we've had stupid parts set us back while compute goes on. The latest one, not to trash a vendor that might have an office here in town, is rear doors for the storage. Rear doors have been a nightmare for this, but the rear chilling doors, talk about the Dell ones, they're a different problem. But the ones we're doing on the storage racks, I ordered them November, December last year. They were supposed to come in February. They actually got loaded onto a ship in Germany in June. That took 5 weeks. By the time they cleared customs, they got to us July 31st. The installers came a week later. Every single one of them was wrong. They're the wrong size and they're missing parts. So 9 months of waiting, none of them work. I know a bunch of rented chillers and really elegant, plastic tube ducts, because we have $100 million in flash sitting there that you can't turn on if you can't chill it. And so I'm explaining to said vendor that the cost of every month of their delay is more than I'm paying them for the doors in terms of the depreciation. So, so they're now worth minus $3 million to me for those doors. So, plus I'm paying $20,000 a month to rent stuff to deal with that. So, but yes, so stupid things are going to set you back on your very expensive machine. So, since I didn't actually mention what's in the very expensive machine, so we have 2 big subsystems in it. The second one's changing a bit because of the memory stuff, but 2,000 GPU nodes, where I'm defining a node here different than I'm going to define it later, but as a Grace Blackwell board, 1 Grace socket, 2 Blackwells. So there are 4,000 GPUs on 2,000 boards, and because they're NVL4 connected, they sit in 1,000 shelves, which is what Dell calls a node in this point. So 4,000 GPUs, 1 to 2,000 nodes, depending on your definition. Definitions are a big problem right now, since we also can't really talk about how fast it is. We'll have a big CPU portion, because it turns out, if you look at my current clusters, despite all the AI hype and everything else, if you look at the GPU queues and the CPU queues, you want to guess which one has the longer wait? If you guess CPU, you are correct, because molecular dynamics people can still fill any queue at any time of any length, as many jobs as you'll let them submit. So so again, depending on which precision you want to measure, whether you count emulation, get into some benchmarks on this, but it's 200 or 300 petaflops. If you think about sort of conventional computing, it's 80 exaflops if you want to think about AI flops in TF4. But somewhere within that range of 500 is the actual performance. You can pick your favorite number. So, and then we have a 400 petabyte VAS file system. It is all InfiniBand, right? Have to talk about InfiniBand here. We've built the non-blocking fat tree. Another trivia controversy: the leaves of a tree go at the top or the bottom. But anyway, that was last night's discussion. But it's an 800 gigabit XDR InfiniBand non-blocking fabric to all those GPUs that is built. CPUs to come that is not built. So those two trees are non-blocking, and then we have an oversubscribed top level that goes about 20 terabytes a second out to the storage. And between those two arrays, nobody's going to run a job that spans those two. But in the end, it's about 9,000 endpoints, 15,000 cables. And again, that CPU portion is built. Other fun, this is the slide I showed with the projected network last year. This is still the slide with the network. The only actual change we've made to this is on these GPU compute nodes where it says those are 3400s. The ones in the core, the 800 gig switches, are 3400s. The ones in the compute racks are 3401s. The difference being that we have AC power going into the switch racks where all the switches sit. You have a DC bus bar in the new racks for the GPUs, so you have to have a DC powered switch. And you would think that it'd be the same switch where you could just pull the power supplies out and put in DC ones. It is not. It is totally different. And one of them is very hard to get. So, because there weren't any for several months. But so it's 3400s and 3401, the difference being one runs on an AC supply and one runs on a DC supply, and apparently a bunch of other differences, even though they work exactly the same. Because again, that's the cheapest way to do it, obviously. So so that remains the network one. The racks themselves, as I mentioned, it's an NVL4 shelf. NVL72 is a sort of whole engineered rack where they put 72 GPUs in a rack and 9U of NVLink switches and 97 power shelves. Because we're not doing the big NVL switches, we're not limited to 72 GPUs in a rack, so we did 144. Shortens your average cable length. It does make the rack weigh 6,000 pounds by the time you put the liquid in the rear doors, which is 2 Honda Civics. I'm from Texas. It's a fairly loaded F-350 you could put on there if you want to do it as a pickup truck. But 2 Honda Civics, by the way, they're 215 kilowatts or so max. So if you actually got 2 electric cars instead, you'd have about 140 kilowatt hours of battery. So you could drive each of those 2 cars 250 miles apiece, or you could run the rack for about 35 minutes before you existed those batteries. So driving them at 70 miles an hour takes less power than running the GPUs. So anyway, again, the Vera racks aren't here yet because they're not actually shipping at this point. Same physical form factor, but about 100 kilowatts per cabinet. We have the 28 GPU racks deployed at this point, and the 34 storage, switching, and management racks are all deployed. For 13 megawatts, we actually started deployment in January. Those are all cartons of flash drives that we couldn't run at the time. The temptation to flip them on eBay, given that $3,000 to $22,000 per flash drive. I'd be giving this talk via Zoom from some non-extradition island had I done that, but the 100 million, the racks are physically just bears. There's Nathaniel again. Turns out they're 9 feet tall. They're more than 9 feet tall on the pallet, and you can only move them on the pallet. So, which is a problem for 9-foot doors. Perhaps that is an improvised door with no ramp in the data center because we had to forklift them directly on. Because you can build a floor that can hold 6,000 pounds, but good luck building a raised floor ramp into your data center. Those can handle 4,000 pounds, so we have to forklift the racks directly onto the floor. But you have to unpallet them in the hall to get them to that door. So on average, Dell would send 10 people to get a rack off a truck, and they could do one every 3 hours with 10 people. Dell's had, on average, 18 people on site for a little more than 4 months at this point, which is probably about 8 times what they budgeted to get the stuff deployed. So they can't be more than a few $100,000 behind. That is some of the underfloor with the secondary loop. We have this thing called the squid. It used to be when you built the CDU, you could go point to point into every rack, but now we have like a 20-degree Celsius delta going in one side of the rack to the other at 200 kilowatts. So if you put 10 racks in sequence, you'd have a 200-degree Celsius delta. In Frontera, we had 30 racks in a line for the CDU loop. That would be a 600-degree Celsius delta. So you'd start with like liquid hydrogen on one end. You could melt aluminum on the other end. So you can't really do that. So you go point to point in and out of each rack. So hence you get this fairly complicated hose system with lots of big hoses. That's some of the switching going in, the tiny little pumps. You get a 1 megawatt CDU cabinet like that. You can run 4 racks off one of those. We have 7 of those on the floor already. They have these tiny little hoses. Sean's also over 6 feet there holding up the 100 and 200 pound flex hoses we have to hook in those CDUs. Those are way too long, by the way. Cabinets of the racks going in as we made it through, sort of starting to evolve. Those are the storage cabinets. Those are the pre-rear door. Compute racks on the right. Just have that for pictures. They are actually sealed, so when you put those front doors on, there's plexiglass behind there. I assume they still have perforated holes just because Dell wanted them to have them look as badly as possible, so they went with a perforated front door and a solid sheet of plexiglass behind it to make it impossible to put graphics on, and yet totally ineffective at moving air because they're in a sealed plenum. So that is the rear door installation going on. You notice it adds about a foot to the rack. I will say those rear doors, when you put them on there, they're 600 pounds empty. They're about 800 pounds when you fill them with fluid. They have their own wheels. When you roll them, if you take something that's 800 pounds and you put it on wheels, and then you open a floor tile and roll it over them, there are really easy to predict things that will occur in that situation that Dell perhaps found hard to predict. So more on that in a second, by the way. Some of the beautiful network cabling Sean and team have done. Those trays are completely full now, but that's all the 800 gig InfiniBand going in. Again, this hasn't really been a linear set of progress, leading Dell to make this warning sticker related to the rear doors, because perhaps you saw that squid with all the valves that you have to open to turn on the rear door and the rack manifolds behind those. But if you open that floor tile and you roll the 800-pound door over it, it will fall in and rip the hinges off the back of the rack. And so Dell decided that they would experimentally determine that at least once, leading them to make this sticker. And when I saw it, which they put all over the floor in the data center, I'm like, I'm embarrassed for whoever you had make this, and I'm going to make sure at least 10,000 people see it. So we're up another 100 today. That's good. I'm getting very close to the goal of having 10,000 people see the sticker. No vendor's ever going to want to work with me ever again. But yeah, I did make a version of this that I thought would explain what was going on to them. So this is my version of the sticker, slightly altered, just to explain the physical principles involved here, that gravity still in fact works. And if you take a wheeled vehicle that's really heavy and you roll it over a giant hole, it falls in. They had a stop work order. They had this whole presentation on safety. They wanted me to screw the floor tiles down. It sort of went like this. I said, one option is I could modify the way the building works, and another one is you could not send morons. But we're still going back and forth on that, so as to the way to deal with this. But I will say, getting those things activated, and they're huge, and they're complicated. They, of course, have firmware that, of course, has bugs. But installing 28 of these, and admittedly, Dell had never built one before. They're their first article. They did send 24 people to do the first one, so they were training people for all over the world to do this. But it took them 10 weeks to get 28 doors in and started after we physically had the doors. So take away the supply chain stuff, still takes them 2.5 months to turn the racks on. But nonetheless, we've managed to build all that out, and we now have all the GPUs there on the floor. Again, 4,000 GPUs deployed, 28 GPU racks, storage management racks, switch racks, CDUs, random rented chillers with random ducts hanging over the top at the moment, so I can cool the storage and actually turn it on. Most of them we've run LinPack tests on. All the storage is tested, but because we've had these cooling issues, we're only mounting a couple of petabytes on the nodes, which has affected some of the benchmarks. So again, we have to figure out how fast it is. So what can we actually do with this? And we've just let the sort of earliest of early users on. DK, I need to get some of your people on this week to do some things, but I have 5 minutes left. So tuning is a lot of work. What we've discovered is between NVLink, InfiniBand, Nickel, MPI, the UCX settings matter a lot. Right? Getting the right hits and the right parameters. And by a lot, I mean like 1,000% faster if you get the settings right versus wrong, 10 to 1 in your scaling plots. But from the networking side, that is the #1 challenge in tuning. Normally, we build a ton of this complexity into all the environment variables we force you to use in Slurm, but I'll show you some of the hints. So when we do benchmarks on these, start with some, I think these are ones that Amit did, who's sitting here. First, you just do low-level things. DK has a bunch on NVL72. Didn't want to steal any of those for this talk, but this is just measuring the Vista nodes for the Graces, and and now we have latency from CPU and GPU in the age of GPU Direct, so you have more parameters to measure out to networks. But and you ask yourself, by the way, you would think all these lines would go straight. So this is latency and bandwidth from the CPU and the GPU on the Hopper versus the Blackwell. The old node, they're both Grace, but the Vista nodes versus the Horizon nodes. Things like cache line size and buffer size and the NIC and stuff like that means these are never straight graceful curves like you'd expect. That one drop, I haven't had a chance to ask Amit about yet. That's something that we might have to look at what is that, 2 to the 18th. So 256 bytes, no, 2 to the 10th is 1,000. So 256 kilobyte messages, there's that drop in performance. But it's probably the multiple of something and something else and how they divide. Drops performance there, but generally as those approach smooth, and we do get twice the bandwidth on the new nodes that we got on the old nodes, approaching the 800 gigabits, you start to say, okay, we have healthy hardware, we have a software stack that can run, we can figure it out. Well, at least on the network side, once you do your micro benchmarks, you run HPL, partially to get the number, but mostly because if you can run HPL for a couple hours, the stuff probably is healthy enough to put users onto it. And if it can't finish HPL runs in a few hours, it's probably not. You have flaky parts. But there's a lot of HPLs now. For high performance LinPack, the thing you rank on the top 500 with, solving systems. This is what the raw output looks like for one of those runs. To see that you're getting right answers, that residual number at the bottom should be very low. There's a whole bunch of discussion of residuals in the age of emulated floating point now. But that's really good. 0.00088 is your root mean squared error message measure here. You have the size of the system. Everything works faster if your matrix is square, as it turns out, if P and Q are roughly the same. The total number of blocks per node, your actual execution time, gigaflops there. So this is a run that cracked 100 petaflops. The first one we did over 100 petaflops on the machine. This was June 26th. Was the first time we cracked 100 on 3,000 of the GPUs, which is what we could cool at the time. And then you see your per GPU number, which says we're getting like 33 teraflops, I think, per GPU. On this one, that number's gone up some as we've had a chance to tune. But so first time we cracked 100 petaflops was in June. So we're getting better at it. This one's 33.5 teraflops per GPU, 125 petaflops total when we were up to 3,700. Find the right nickel library. You don't get one of these benchmarks back without comments from staff about what was broken in the software stack, and those everybody's going to know who this is, who knows us, but but I always get a little editorial along with it when they run the benchmark. So they say things like stupid OpenMPI doesn't propagate all the right variables for the UCX settings, so I had to specify them to be exported on the MPI run command line. Again, all things we'll build in before we give it to the users, but it's messy. So, but this is what sort of the bring up process looks like. But now we used to just have HPL. Now we have 3 HPLs, so that's fun too, right? So native, that was 3,700 GPUs. We're going to hit about 130 petaflops. We're getting about 84% peak efficiency, so that's pretty nice. That's 5 petaflops per rack. That's ridiculous when you think about it. In the first cluster, we were trying to build 50 gigaflop for $50,000, which would have meant 5 petaflops would cost $250 billion back then. Of course, the AI budget is actually larger than that now, but still, 5 petaflops a rack is just a crazy number. But 130 for those 28. You lose a little bit at scale. For emulated HPL with the Ozaki 2 method, which we have a nice NVIDIA library for now, just do Ozaki 1, you get about double. We're getting about 2.5 for the Ozaki 2. So I can also get a number that has just as good a residual in LinPack running this. And this is for how many GPUs? 22 petaflops on 256 GPUs, right? So I'm getting 88.5 teraflops per GPU. So up from 33. Running emulated, we have a few codes where we're starting to see pretty good real speedups from Ozaki method. There's questions about dynamic range, but so far it seems good. So that should get us to the, we have runs in over 200 petaflops. We cracked 200 petaflops. The scaling is not quite as good, so we're looking at some network things, but we should get to about 300 petaflops with Ozaki. So 130 native, 300 with Ozaki, just the GPU part of the system. None of the CPU's nodes are even there yet. With mixed precision, HPL MXP, where you still get a 64-bit answer, but you're doing some of the internal iterations at 32, 16, and 8, we're getting 80 petaflops a rack at the moment. So I have some NVIDIA folks on there right now. Started last night. We're trying to pull 2 exaflops out of the system on 28 cabinets, so, which is also absurd. And then, of course, the AI flops number is more like 80 exaflops. So how do you tell someone how fast the system is, given I can generate any benchmark number you want out of it, pretty much legitimately, depending on the precision you're willing to use and whether or not you emulate. So perhaps we ought to focus on what it can actually do scientifically as the answer. I promise I will stop soon, DK. If you do all this HPL and low-level benchmarking and everything else, it does not ensure your applications run well, but it helps. There are other things that can go wrong and often do. But for the most part, things that aren't I/O intensive, because the rented chillers just went online to turn on the rest of the storage racks. So we know I/O is terrible, but again, we start out with a bunch of things that need tuning, mostly UCX settings. When we get a good MVAPITch, I think it'll get even better. But I'm getting good numbers, although the way my staff report numbers need to do a little translation. But like Sysol seismic code, originally out of Germany, it was one of the best scaling CPU codes we ever saw, but when we started on it, it was a pure CPU code. And again, our metric for science was to deliver 10 times the throughput of Frontera when we started the project. So here's the actual numbers. It said in 394 seconds with what we could do with 4,000 Frontera nodes versus 100 Horizon NVL4 shelves, right? So my translation of these numbers is I can take a code that used to only run on CPUs, and in the same fixed time, we can run a problem that used to take half of the old Frontera system, and that should say Horizon GPUs, but we can run it on 10% of the Horizon GPUs. About half the money went into the GPU side versus the CPU side, so it's 10% of half the system, so 5% of the system. So we get roughly 10x the throughput for this particular code that we got out of the old machine, including doing a port. The CPU speed up's actually better. So here's another code. For some reason, I picked mostly earthquake ones. AWP, this is Yifeng Hui's code. Actually, he's done a lot of work with you guys in MVAPITch. He talked here last year, but out of San Diego. So in this one, we're doing sort of a weak scaling example, but we scaled the model because things we could run on Frontera, part of Horizon is to do bigger problems, right? So, and in this one, you can see the raw run times, the size of the matrices. But what we did is run a model that's 16 times larger, from 3,200 Frontera nodes to 350 Horizon GPU shelves. I know from some other measurements that about 300 seconds of that will disappear when we give it a real file system, because it's a little more than 10% I/O. So we'll get it down to about 2,600 versus 2,400. So again, 3D finite difference code does multi-rupture earthquake, more than one fault going at the same time. So this says with 35% of the Horizon GPUs, we can run a 16x bigger model than we could with about 40% of all the nodes on Frontera. Again, GPUs are about half, so we have about 30 times the throughput on this code than we had, sort of per dollar or per flop. If we loaded the system with runs this size, I could get 30 times as many runs through on Horizon in a given month as I could on Frontera. So these are probably the better measures of what we ought to do. So I'm out of time, so let me wrap up. So what's left for us to do as the GPU system gets healthier and we start to add users to it, but we still have to do the CPU component. It's not going to be the number of nodes I had there, thanks to the market, but I think we're still going to end up in the 4,000 nodes, 700,000 core range on the Vera side for those next-gen CPUs when NVIDIA gets them shipping in quantity, which hasn't happened yet. Once we get users over to Horizon, we're going to steal some of Vista to build 2 other systems. One is the Kubernetes partition for Horizon that'll run services and Jupyter notebooks and the interactive piece. But the other one is a new system that we haven't formally announced yet, but it's far enough along that I'll say it, called Sagebrush, which will be our inference platform. It'll have some Samba Nova racks, and then we'll repurpose some of those Hopper nodes to be those dedicated things to run chatbots. We're going to add some fast KV and RAG storage to it. So we'll build an inference system, an interactive system, and a CPU system in addition to the GPU system we have now. We still need to figure out the node sharing, but I'm not going to let one SU be a full NVL4 shelf, because then if somebody takes an hour to run their Python script on one core, instead of wasting a $6,000 node, they're wasting a $200,000 node for that hour. So nodes last 40,000 hours over 5 years, so do the math. We have to start operations. We have found that the old CPU nodes, no one wants to get off of. They're still full. Frontera is still full. It's got 40 days left in its life. So for those of you who run on there, we have 8,000 of those old compute nodes. The storage is falling apart, so we're going to turn that off. But you'll probably see those nodes pop up on our OPA system, Stampede 3, and the old Skylake partition go away there. We're going to run those nodes till they die, because CPU time is valuable. They're way less power and way less cost than buying new CPU nodes. So we'll keep that going. So, by the way, this is totally a bubble, so it will pass. Quick note on data centers that I've written for legislators for the most part, but this is not a UT official slide. This is my opinion. All of this is my opinion, but particularly on data centers. Power usage is a really big concern about data centers and what they're doing to the grid. It's 100% a legit concern. Carbon from it, they're using simple turbines where they're adding their own natural gas, which uses twice as much as carbon as combined cycle natural gas turbines, et cetera, et cetera. There's some things you can do here with regulation that would help. Water usage doesn't have to be a concern for big data centers. If you build them right, there are a few examples. Noise and health is the same thing, where people just blow air through at 40 miles an hour to open vents on the other side. But if you stand outside the back wall of our data center at Rock, in Round Rock, either one, Rock is the one in Austin, you can't tell if it's on or not. There's no sound, there's no low frequency component, there's no nothing. Again, there are places where there are bad data centers where that may be a concern, but that's mostly hype. The land use is nothing. The promises of jobs are mostly lies, because they're only for construction. So if people are asking for tax incentives around how many jobs they create, I'll keep 4 people in Round Rock. I'm going to run that data center. So last thing, the world we live in is, the funding context is not that pretty. Some things we can do. We can't individually move that. If you do get money, you can't buy much, and it won't ever show up until the bubble bursts. That's reality. That's what we live with. There is stuff we can do in this context to still be effective. So again, my opinion of what we need to do. One is, we need to squeeze every ounce of performance out of what we have. We are in a culture where they're spending money just to build the biggest model, $1 trillion a year. There's not a whole lot of focus on efficiency. You've heard me talk about this before, but software and algorithms, mixed precision, emulation, how we're going to use all that stuff, compression on the network, et cetera. We can get a lot more performance out of this very expensive hardware, and we need to do it. And that you don't need $100 million in hardware to figure out how to optimize this stuff. And that's something every academic project can work on. We need to squeeze all the life out of the hardware, right? So, repurposing without buying support, those Frontera nodes to run a throughput queue on Stampede. But, figure out where you can live without paying for support, or creatively repurpose things. The argument used to be we turn off nodes at 5 or 6 years because my new nodes put out half the carbon for twice the performance at the same cost and the same power. But a new CPU node uses like 4 times the power and 5 times the money of an old one. Even though it's 4 or 5 times the performance. And per core, it's pretty damn close to the same. So Frontera is on year 7. We're going to try and push those nodes to year 9. Because why turn off a 300-watt node to replace it with a 1,200-watt node that's 4 times faster? There's no environmental argument on that anymore. We have way too few vendor options. There's a lot of startups here. In the AI ecosystem, I wouldn't call AMD a startup, but nonetheless, a lot of the software stack is sort of built around a monoculture. We need to support good alternatives in the marketplace, and maybe experimenting with them, one, because they're willing to be more aggressive, is a place we can help. We need to buy their stuff. That's one thing we can do, but show them the real barriers I mean, I keep stressing to AMD, it's not CUDA, it's all the AI libraries built on top of CUDA that are their problem. And they need way more people working on that stuff. But, figure out what's keeping them from there. But again, mostly getting good software that we can build and put out on multiple platforms will be key to making a bigger vendor ecospace, which is where we're going to get there. And we are going to have to continue to work with the clouds. If you're not working with the clouds, we're going to have to do more of that. But our users are going to pay a fortune for it. So we have to do the same sort of optimization. Good software is the message to get the most out of every cloud hour we pay for and leverage all those shared resources. Now I'm sure I'm over time, so I will stop there. And thank you very much.
So we have time for a few questions.
No matter how long I talk, he's going to figure out a few questions to not let me have that.
From here as well as online? Yeah, please.
Go ahead. Yeah.
If cloud is so expensive and users have to go there anyway, does it make sense, or is it even possible for you or a combined way to set aside some compute for cloud so that you get back some of your money?
You mean to do cloud style computing on our infrastructure?
To be a server for other people.
Yeah. Most of what we do already offloads the cloud in a lot of ways, right? People come to us first, and when we can't give them enough compute for free, paid for by others, through the agencies, the next thing we can do is send them to the cloud to pay, right? So to first extent, every cycle we put out is in some ways offloading the cloud, right? And everything we do on-prem. We have looked at sort of matching the software stacks, projects like Jetstream and Chameleon, where we have cloud style resources where the interface is the same. I think we're going to have to do more of that. But what we found in the AI space is really it's container support, right? And if we have good support for containers, they don't really care if they're on the cloud or not, right? Because they're going to run a VM in the cloud and put a container on it with their standard AI build, because otherwise building the software takes the rest of your natural life. If we can run the same container on our infrastructure, then they can move back and forth. Data migration is still a huge problem. But as long as we support containers, we found that's sort of the main barrier for users to say, sometimes I run in the cloud, and sometimes I run with you. Yeah, I'm back.
So when we're post bubble, the prices are going to drop, but the funding is going to dry up equally or arguably worse. Are we prepared for that?
No, that's an easy question. No, I think prices could drop a lot. The problem is I don't know when that's going to be, right? Right now, plans for next year's spending are much higher than this year's spending. So, it could be in a month, it could be in 2 years, it could be in 3 years. If I knew, again, large non-extradition island. But yes, there will be a disillusionment with AI funding. My hope is that perhaps we will do real science funding again at that point, and we'll at least get back to where we were on a funding. Given the state of federal finance, it's hard to believe that we'll ever go back up substantially, but we might be able to get back to the status quo. But if we can get to the status quo again, but buy stuff for 10 cents on the dollar, at some point we're gonna have to think about buying stuff that's not brand new too, because when there is the opportunity to go find a data center that went out of business with 2-year-old GPUs at 10 cents on the dollar, we might want to do that. Typically, we don't have that kind of purchasing flexibility, but we're going to need to find it.
Here.
Last one. Yeah.
Thanks, Dan. This was a great presentation. Do you offer, you basically offer GPU as a service?
Yeah. So, we're still running in sort of the HPC model. So it's a Slurm queue with GPU nodes, but you could think of it that way. Yeah.
So do you compete with any of the new clouds?
I wouldn't say we compete with them because, to get on our systems, it's peer-reviewed open science that you have to publish. You have to apply for an allocation we don't just take random startup. I want to train a model to make money on and give them time. But arguably, our customers are looking, the academic users that we serve are looking for compute anywhere they can get it, and one place they can get it is the neo clouds. We have an awful lot in common with them. An awful lot of my staff have gone to work for them because of the way things operate, the core weaves and Nebiuses of the world. So.
Yeah, so outside the top few like CoreWeave and Nebius,
Mhm.
there are over 200 new clouds, and
Yeah.
most of them, other than the few top ones, have a stranded compute issue. Like their GPUs are 30% utilized.
Mhm.
So does it make sense to leverage them in terms of some of the compute need?
If we can find a way, most of them are sort of stranded for a reason. Network is one, data transport, right? If you're sitting on our system and you have 5 petabytes on Scratch, throwing you over to, move your 5 petabytes to one of those is why they're stranded in the first place, right? So, also the models for sharing, aren't great, right? There's a lot of underutilization of GPU cycles, but I mean, for the most part, multi-tenancy messes with reproducibility of results in terms of performance, has been a non-starter for both them and for us. But I think there are opportunities there if you can find a cheap way to transparently harvest those cycles, but it's been making it transparent that's never worked, sort of in history. But we're getting better at abstracting some of these things, so perhaps. Mhm.
Yeah, let's have the last question.
Okay.
From Charles. Yeah.
Do you
Oh,
have
I
like
can
a, do you have a Dan's guide to building a supercomputer in, 2026? I mean, this is so,
I think Dan's guide in 2026 is don't, because it hasn't been fun
Yeah.
this year, but the wait for 2028 might be my guide. Don't really, but we do have a HPC leadership course and the occasional admin course that I've contributed a bunch of slides to over the years that have some of this. And then, I do this. You can find me on YouTube. Yeah, but not really. So one day I'll write a book when I'm not hopelessly behind on government reports. My primary creative writing instance. Yeah.
part of this insanity, right? So it's
Yeah.
communicate the learnings to everybody else.
Yep. I try and go rant about it at conferences for the most part. Yeah. Here.
Okay, so let's give a big hands to